All right. So, yeah, hi everybody, and I'd like to thank the organizers for the opportunity to talk today. Uh, the topic of my presentation is on how we're starting to integrate more and more Earth observation data, remote sensing, satellite-based data in our calibration, validation, and application of very large-scale, fully integrated groundwater, surface water models. And while I'm presenting, really, the work that I'm showing is the contribution from a large group of people. Uh, so Canada One Water Hazen already kind of showed the team, and there are a lot of experts on a lot of different facets of Earth system science here, and a lot of them are contributing to how we're utilizing the remote sensing data. Specifically today, uh, we'll talk about work that John Crowley has led at the Surveyor General. Tariq Aziz, who was a postdoc at Aquanti for a while, led while he was here, and work that Omar here at Aquanti has led in terms of model development. So, and others have contributed as well. So while I'm presenting, it really reflects the contributions of a large team. So the remote sensing products that we're going to discuss their application of today, there's 5 of them. The first is Landsat. So Landsat was launched in 1972, and it's given us pretty consistent Earth imagery since then. It has about an 18-day revisit time and operates on various spatial resolutions, but on average, the multispectral sensor is about 75 meters. We also use MODIS data. So there's 2 MODIS satellites. One was launched in 1999, the other in 2002, or I should say MODIS sensors on satellites, 250 meter to 1,000 meter resolution, 1 to 2 day revisit time. GRACE, which is John Crowley's real contribution to the work I'm showcasing today, launched in 2002, runs at 300 kilometer spatial resolution with a 30-day revisit time. The soil moisture data, and I should mention Jiayang Zhu at University of Toronto. He really kind of led the development of the integration of SMAP soil moisture data into our large-scale modeling. We're using the 9-kilometer resolution version of that data product with a 2 to 3 day revisit time. And then more recently, we are starting to integrate the SWOT, the surface water ocean topography data into our workflows, and that's a 50-meter resolution with 11-day revisit time. So I'll get right into it. And I've got 4 case studies that we'll talk about. So the first case study is looking at how we assess surface water extent in a fully integrated groundwater surface water model. So one of the benefits of using a model like hydrogeosphere, where we dynamically couple the groundwater and surface water systems, is that where the groundwater expresses itself at surface, we can pick up that surface water representation as an analog for groundwater position at the points where we have surface water in the model. And the example we're looking at here, this is a watershed up north in the Canadian Shield. It's about 3,500 square kilometers, and it's in a region with a lot of small lakes. And while there wasn't a lot of groundwater monitoring data that we could use, there were many, many lakes, and we modeled the bathymetry of those lakes and stitched the bathymetry into our digital elevation model to create a digital terrain model. So then when we run the model, those lakes fill up with water. And if the aerial extent of the lake is accurate, then we have a reasonable expectation that in the area where we have lakes in the model, we're also resolving groundwater position reasonably well. And where we have lakes, like hundreds of lakes over a model domain, we actually have a pretty good ability to capture the shallow groundwater elevation. So this is an example where we have a model. It runs at about, I think in the vicinity of the lakes, we had about 125 meter resolution. The Landsat imagery that we were basing the surface water extent on was 30 meter resolution. So we build the model, we spin it up, we get water in the lakes, and then we start looking at how well do we match the surface water extent in the model with surface water extent uh, as determined through this historic imagery data that we use. So here on the left, panel A, this is surface water extent derived from Landsat. We use a data product called the ESA Global Surface Water Explorer. It's described in this Nature paper, heavily cited over the years. So we have, this is kind of our benchmark for where we want to see surface water in the model. And panel B, this is the modeled surface water extent. And when we do some statistical evaluation of surface water inundated pixels in our model versus surface water inundated pixels in the Landsat imagery, we can see with various renditions of the model, we get close to, but not quite at 100% of the surface water representation. So this is a mechanism for calibrating and validating large-scale models where we don't necessarily have groundwater monitoring data available, or if we do have groundwater monitoring data, it tends to be sparse and allows us to benchmark a specific location or a number of like discrete locations, but it's not spatially extensive. So when we revert to the surface water mapping, we can get an extensive perspective on our ability to pick up groundwater levels via the surface water proxy. Now, that Landsat data is the precursor to what we're doing now with the SWOT satellite data. So the SWOT, which was launched in 2022, that is actually giving us surface water elevation. So time varying surface water elevation, as well as surface water extent. So the Landsat imagery is relatively static. So when we look at this type of a map for model validation purposes, it's kind of a static representation of our surface water and groundwater conditions in the model. But with the new SWOT data that we're starting to integrate into our workflows, we will get a transient perspective on surface water variation, the elevation fluctuations with time, and we can use that then as an analog for groundwater fluctuations with time. So we can turn this kind of a static perspective of model validation into a transient model validation mechanism. So the next case study I'm going to look at, and this is really John Crowley's leading, is the integration of GRACE data with large-scale fully integrated groundwater surface water modeling in order to track changes in subsurface water storage, as well as surface water storage and snowpack water storage. So again, with the fully integrated groundwater surface water model, we've got all the primary terrestrial components of the water storage. So we've got snowpack, we've got surface water, we've got soil water, we've got water in the superficial hydrostratigraphic layers, and then we've got water in the deeper bedrock layers. So whereas GRACE gives us a single signal for water storage variability, we can use hydrogeosphere to decompose that signal into the various components associated with the different water storage compartments. And if we just look here on the panels on the right, you can see that the big picture correlation between HGS and GRACE is very good. So that indicates that hydrogeosphere is capturing quite nicely the total water storage change over time. This case is the Southern Ontario model domain. And then we can break down that hydrogeosphere signal into the different components associated with surface water and soil water storage variability, and then storage variability in the quaternary and bedrock layers. And what's interesting is you can see the interannual variability that's largely associated with the surface water and soil compartments. But then you have these longer decadal signals that operate kind of on a much longer time frame that are associated with storage changes in the quaternary and bedrock. And that correlates with the different frequencies we see in the signal in the kind of that aggregate signal we're getting out of GRACE. So a really good way to corroborate water storage change that we're detecting in the fully integrated groundwater surface water modeling against a remote sensing based product. And again, the use of GRACE, well suited for large scale models. The resolution of GRACE is relatively coarse, but these large scale models that we're running, they tend to have relatively coarse resolution as well. So that was case study number 2. Case study number 3 is our use of soil moisture data from the SMAP satellite. So SMAP was launched a while ago. It was supposed to have an active radar sensor as well as the passive radiometer. Unfortunately, for those of us in the soil science community, the active radar sensor power supply died shortly after launch. So SMAP really became SMP. So the passive signals we're getting from SMAP are still useful, but just not as highly resolved as what we would have seen from the signals coming out of the active radar sensor. So this case study that we're looking at focuses on the 4,000 square kilometer South Nation River watershed in Eastern Ontario. We built a model, collaboration with the South Nation Conservation Authority, Agriculture Canada, and the Geological Survey of Canada to simulate groundwater surface water flow processes in this area. And we've subsequently used that model to do a lot of other things, including correlate our soil moisture against remotely sensed soil moisture. And very good spatial distribution of model performance across this domain. And we also had groundwater levels calibrated, so we have good, generally good ability to reproduce groundwater levels in the watershed. And we had a few discrete points where we were able to obtain soil moisture measurements from Agriculture Canada. So Agriculture Canada has one of their RISMA benchmark stations in the watershed, so we can use that data to benchmark hydrogeosphere simulations, but we can also benchmark the remote sensing SMAP-based data. And the time series figures we see on the left here, this just shows the correlation between the blue line, which is the simulated soil moisture from the HGS model, the black dots, which are the SMAP observations, and the red lines, which are the continuous in situ soil moisture measurements from the RISMA sensors. And we have this at different depths as well. So generally good correlation between HGS, RISMA, and SMAP. But the beauty now is that with the benchmarking done at these discrete points, we have an idea of how well SMAP behaves and how well HGS behaves across the entire watershed. So if we look at these 9-kilometer pixels that are broken down in this center column of figures, these are the individual pixels where we did further correlation between hydrogeosphere and SMAP. And from that correlation and the prediction of water storage changes in hydrogeosphere, we were able to determine the latency between soil moisture fluctuations that were observed in SMAP and the water storage changes observed in hydrogeosphere. And what we see is, and this corroborates with other information in the literature, but now we can essentially turn fully integrated groundwater surface water models into a prediction tool for this, is that as we see soil moisture fluctuating, that soil moisture fluctuation is going to impart a latent signal response into subsurface storage changes. And as we move deeper down into the subsurface, we see a longer lag time between the surface soil moisture fluctuation and changes in subsurface storage. And from this, we can start to infer that we can predict deeper groundwater storage changes based on shorter term signals we're observing near surface. And as we get down into the deeper subsurface, we're moving towards upwards of 12 days of lag between what we see in subsurface storage fluctuation and the superficial soil moisture fluctuation. And this is published in a recently released paper, if anyone was interested. The fourth case study I'm going to look at is our use of MODIS data that has been converted to geophysical quantities associated with biomass. So MODIS, it's a multispectral sensor. That sensor data can be translated into different physical quantities based on algorithms that uh, people derive, and one of the quantities is biomass. And biomass is associated with ecosystem services. So as we're producing biomass in these watersheds, that biomass represents the contribution of water to ecosystem service production. And when you look at the different components of a fully integrated groundwater surface water simulation, which I show here in the figure, all of these water fluxes can ultimately be characterized in terms of their contribution to ecosystem services, and ecosystem services can be economically valued. So that was the purpose of this study. So we have our fully integrated groundwater surface water model, again for the South Nation watershed. And this time what we're using it for is to produce long-term predictions of storage change and changes in annual water fluxes in response to varying climate and weather patterns. So from 2000 to 2017, we have a transient simulation that we aggregated into annual chunks. And within these annual chunks, we see differences relative to the long-term mean in evapotranspiration, precipitation, subsurface water storage change, and surface water storage changes. And these anomalies correlate with the variation in climatology. And what we see, to make a long story short here, is that in this particular watershed, during extreme drought years, so 2012 was a really interesting year to study. It was an extreme drought, not just in Eastern Ontario, but a lot of the Northwest was under drought at that, or the Northeast was under drought at that point. So we use this as kind of a benchmark year for analysis. And what we see from the biomass production is that in general, the biomass that was produced in the landscape didn't take as much of a hit as you would have otherwise thought based on climatology. Now, the reason why that biomass production was sustained was the groundwater contribution to that biomass production. And that groundwater contribution can then be valued because biomass can be valued through its ecosystem service value. And through the analysis we did in this particular paper, which is just in press now, can see that in 2012, there's upwards of $400 million worth of groundwater contribution to ecosystem services associated with biomass production, and that's otherwise a drought year. So, very interesting connection between using remote sensing to characterize ecosystem services, relating the water production and water cycle that we see in the fully integrated groundwater surface water model to the water consumed for biomass production, and then in turn putting an economic value on it. So we can, succinctly state that the groundwater contributions to ecosystem services are worth a fortune. And this is a 4,000 square kilometer watershed with about a $400 million contribution from groundwater to ecosystem service production. So really interesting numbers, and numbers that support the value of groundwater to society. So in summary, we can state that remote sensing data products, they can help us constrain large models for validation, calibration purposes. Soon we'll be able to use these remote sensing products for transient calibration and transient assessments. The groundwater surface water models can aid in our interpretation of remotely sensed signals from these Earth observation sensors. And they can also, and this is what we're getting at now in Canada One Water Phase 2, they can help with the initialization of these large-scale groundwater surface water models for groundwater forecasting applications, because Earth observation data cannot look into the future, whereas the models can. So with that, I'll end it. I think maybe I'm on time. I'm not sure. Back to you, Don.